Hey guys, welcome back to another lecture video for Chem 115. In the past two lecture videos, we have discussed what rate laws are, as well as orders of reaction. In addition, we learned how to write a complete rate law for any given chemical reaction by employing the method of initial rates. In this lecture video, we are going to understand what it means for a chemical reaction to follow first order, second order, and zero order kinetics. We will also discuss what characteristics they express when we look at their half-lives, and when the rate law is integrated. So let's go ahead and get started. The first thing that we're going to do is write the rate law for a chemical reaction that's undergoing first order kinetics. Now, for first order, second order, and zero order kinetics in this course, we are only going to focus on chemical reactions that contains only one reactant. And the reason for this will be better explained when we start talking about integrated rate laws. So I want you guys to go ahead and keep in the back of your mind a general chemical reaction that only has one reactant, such that alpha is going to represent the coefficient for reactant A. And reactant A is going to undergo some type of decay or decomposition to produce products, whatever they are. And so if a chemical reaction that contains only one reactant is undergoing first order kinetics, the rate law can be written such that the rate of reaction is equal to the rate constant K times this by the concentration of reactant A raised to the first power. Now, reactant A is going to represent any chemical, any reactant that undergoes some type of decay or decomposition. And so what we want to address is what it means for a reactant or reaction to be first order. All right, so what does it mean to have a first order kinetics or to follow first order kinetics? And so the best way to address that question is to look at how the rate of the chemical reaction changes by differing the concentration of the reactant. And so here, if we take this reactant to be reactant A, what would the relative rate of reaction be if the concentration of reactant A is equal to 1.0 molar? And so what we're going to do is we're going to take this general rate law and we're going to plug in this concentration value into A. And so therefore the rate of the chemical reaction is equal to some rate constant K times this by the concentration of 1.0 raised to the first power. And so there's a reason why I did put in relative rate instead of the exact rate of reaction. Since the rate constant K is currently unknown, we're going to go ahead and exclude it. And we can go ahead and exclude the rate constant K because it's a constant. That number, this number right here, will not change. And so once we determine the value of rate constant K, then we can actually figure out what the exact rate of the chemical reaction is. And so I'm going to go ahead and just exclude this constant. And by excluding that constant, I'm just now referring to the relative rate of the reaction. And so if I were to raise 1.0 to the first power, because it's undergoing first order kinetics, the relative rate is going to be 1.0 molarity per second. And so what would happen to the relative rate of reaction if the concentration of A doubles? or it goes from 1.0 to 2.0? Well, we can go ahead and plug 2.0 into the general rate law. And once again, we're going to exclude k so that we can express this in terms of relative rates. And that's going to be 2.0 raised to the first power. Now, 2.0 raised to the first power is going to be 2.0 molarity per second. Okay. Now, if you guys follow this logic, the relative rate is going to be 3.0 when the concentration is 3.0 molar, and 4.0 molarity per second when the concentration is 4.0. Okay? And so basically what this is telling us is that if we double the concentration of reactant A, we are doubling the rate of the reaction. If we triple the concentration of reactant A, we triple the rate of reaction. And so if we quadruple the concentration of reactant A, we quadruple the rate of the reaction. And so if a chemical reaction behaves in this manner, such that doubling the concentration doubles the rate of reaction, then it's following first order kinetics. And so I wrote a little blurb here that you guys can go ahead and read. But basically, this trend that we're observing from comparing the concentration of reactant A to the rate of reaction it's pretty linear, it's pretty simple. So basically, if the concentration doubles, then the rate of reaction doubles. If the concentration triples, then the rate of reaction triples, and so on and so on and so on. Cool. And so that's basically what it means for a chemical reaction to undergo first order kinetics. Now, what we're going to take a look at is the kinetic data for first order reactions. And what we're going to look at is the how this kinetic data looks like when we plot the concentration of reactant A against time. And so it turns out that we're going to get an exponential decay. And I've already brought up this point in an earlier lecture video. And so I'm going to go ahead and zoom in on this graph that's already pre-made for you. And so I want you guys to notice that the concentration, moles per liter or molarity, of reactant A is on the y-axis because it is a dependent variable, and time is an independent variable, so therefore it's on the x-axis. And so if we plot concentration against time, we get this exponential decay that is observed here. And so in a very superficial level, that's pretty much all that we can get out of this. However, if we start looking at this concentration versus time graph in terms of, for example, half-lives, we're going to see another characteristic of first order kinetics that's not observed by simply looking at this table. And so before we continue, we need to define what half-lives are. And this is a very important topic in kinetics. So a half-life is basically the time, okay, so the half-life is referring to time it takes for the concentration of that substance to fall exactly to half of its original value, or previous value if you're talking about consecutive half-lives. All right? And so how can we apply this definition of half-lives in terms of a graph? Well, if the initial concentration is 2.0 molar, or I'm sorry, 0.20 molar, half of 0.20 molar is going to be 0.10. So remember, for a half-life, we're talking about the time it takes for the concentration to reach half of its initial or original value. Okay? And so when you're looking at the first half-life, you're going from 100% of the reactant to 50% of the reactant. And you want to know how long it takes for it to go from 100% to 50%, or in this case, 0.20 and 0.10. And so what we're going to do is we are going to basically expand or write a line. See if I can do this better. I'm going to create a line. And so notice that when this black line touches this exponential decay graph, this green line, it's going to tell us how much time it took for the original value to reach half of its original concentration, right? And so if the original concentration is 0.20, then the time is going to be, let me back that up. Then the time is going to be 0, okay? And so if we go from 100% to 50%, the time it took is going to be approximately 7 seconds. And so this is going to be the half-life. Specifically, the first half-life. And so it took 7 seconds for the reaction to go from 100% to 50% of reactant remaining. Now, it's great that we're able to determine the first half-life, or the time it takes for the initial concentration to reach half of its initial value. But for us to better understand this characteristic of half-lives with respect to first-order kinetics, we need to look at consecutive half-lives. And so the second half-life is going to start at 0.10, and once again we're going to take half of this value, which is going to be 0.05. And so when the concentration reaches 0.05, how much time did it take for the remaining value to reach half of its, for it to be halved? And so if I extrapolate that line downwards, notice that here, so this is 14 seconds. And so this right here is 7 seconds. And so if I calculate the difference between 14 and 7, the second half-life is going to be 7 seconds as well. Okay? And so here we see a trend if we look at the first half-life and the second half-life. We see that the time it takes for the concentration to reach half of its value is going to be the same. So the first half-life and the second half-life is going to take the same amount of time. Now, if you guys do this for the third half-life, so half of 0.05 is going to be 0.025, so that's going to be somewhere around here. Okay. And so the graph doesn't really go too far, but I'll go ahead and tell you right now that if we expand this by one more space, in other words, it's going to be 21 seconds. The third half-life is still going to take 7 seconds. And so this is something that's very characteristic of first-order reactions with respect to half-lives. And that is that the first and all consecutive half-lives will be the same, will have the same amount of time. 7 seconds, 7 seconds, 7 seconds, 7 seconds, and the list continues. And so it turns out, and I'm going to go ahead and tell you how this equation was derived later on in this lecture video. And so it turns out that the equation for a first order half-life can be described as T1 half is equal to the natural log of 2 over the rate constant K. And so whenever you guys see T1 half, I'll go ahead and rewrite it. This is describing the half-life, the time it takes for the concentration, for the initial concentration or the original concentration to reach half of its original value. So T1 half is just a symbol to represent half-life. And the unit for half-life is typically in seconds or minutes or hours. It just really depends on how long, it really depends on the time scale. And so it turns out that if you were to take the natural log of 2 and you divide it by the rate constant K, you'll be able to determine the half-life or the time it takes for the original concentration to reach half of its value. Okay. And so what is the implication for this, this half-life? And so it turns out that since the concentration of the reactant A, or any reactant really, is not present in this half-life equation, this is telling us that the half-life is independent of the concentration of the reactant. And so this is the reason why all consecutive half-lives will be the same. In other words, here we have 7 seconds for the first half-life, 7 seconds for the second half-life, and 7 seconds for the third half-life. Okay? And so right now, this implication might not mean anything to you guys right now, but when we start talking about second order and zero order half-lives, you'll see how the dependency of the reactant will change the time it takes for the concentration to reach half of its value, in addition to the consecutive half-lives. Okay. And so right now, just go ahead and keep in the back of your head, or back of your mind, that all consecutive half-lives will be the same for first-order reactions. That's really the take-home message. And the reason why is because this half-life equation is independent of the concentration of the reactant. And so whatever remains doesn't affect the time it takes for the remaining amount of reactant to reach half of its value. All right, so I want you guys to recall that the rate constant K, the units for the rate constant K, will always change, and it really depends on the order of reaction. And so another characteristic of first order kinetics is looking at the units for the rate constant K. And this can be derived by looking at the units, This can be derived by looking at the units from the half-life equation. So T1 half is equal to the natural log of 2 over K. And so to determine the units for the rate constant K, we're first going to solve for K. And we can do so by multiplying K to the other side, so that this cancels. And I get K times T1 half, or the half-life, is equal to the natural log of 2. Now to solve for K, I need to divide T1 half to the other side. So therefore the rate constant K is equal to the natural log of 2 over T1 half. Now, there is no unit for natural log of 2. And so what we're going to do, let me take a step back here. So now that we solve for the rate constant K, we're going to replace both of these terms, natural log of 2 and T1 half, with the unit they represent. And so since natural log of 2 is unitless, that can be replaced by writing down 1. So the natural log of 2 is not 1. What we're looking at here is the unit that they represent. So this is unitless. Okay. And so therefore we can just go ahead and represent a term that's unitless as just 1. Now remember, t1 half, it doesn't mean half of t. This is representing half-life. And half-life is always expressed in time units. In this case, it's going to be seconds or minutes or hours. Just really depends on the time scale of the reaction. And so if the time scale of the reaction happens to be in seconds, then therefore the unit for the rate constant K is equal to 1 over S. And so you have three different things that can indicate if a chemical reaction is undergoing first order kinetics. One, you can look at the unit for the rate constant K. So if it is 1 per second or 1 per minute or 1 per hour, that's indicative of first order kinetics. If the first half-life and all consecutive half-lives have the same time interval, that's also indicative of first order kinetics. If the equation for the half-life is t1 half is equal to natural log of 2 over k, then it's also indicative of first order kinetics. Here, if you have a general exponential decay, that's indicative of first order kinetics, but this isn't actually a good way to determine if it's first order or not. And you'll see it when we look at second order. So last but not least, when if you double the concentration, and if the relative rate of the reaction doubles or triples in the correct proportion, then that's also indicative of first order kinetics. And so if you triple the concentration, you triple the rate of the reaction. If you quadruple the concentration, you quadruple the rate of reaction. Okay? So all of these are characteristics of first order kinetics. And so the first order kinetics can be observed in, for example, pharmacology. And so if you want to talk about the rate of elimination of drugs, it's typically proportional to plasma concentration, such that if you have 80 milligrams of a drug, if you were to calculate its half-life, so it's t1 half, and if you were to calculate all consecutive half-lives, the amount of time it takes for the concentration to reach half of its original value is going to be the same. So for example, this could be 7 seconds, this can be 7 seconds, 7 seconds, 7 seconds. And so the elimination of pharmaceutical drugs within therapeutic ranges typically follows first order kinetics. Another example of a reaction that undergoes first order kinetics is the decay of radioactive isotopes. And so if you have a singular nuclear atom, and if it's radioactive, its decay can be described by first order kinetics, such that if you have 100% of this radioactive isotope material, and if you were to plot its concentration against, percentage of isotopes remaining, or amount remaining, against the number of half-lives, the amount of time it takes for its concentration to reach half of its initial value is going to be the same. So the amount of time here, the t1 half, is the same as the amount of time here, as well as the amount of time here. Okay. All right. So hopefully with that said, you guys have a better understanding of first order kinetics. Now let's go ahead and talk about second order kinetics. Very similar to first order kinetics, we're going to assume that we're only working with one reactant. And the reason for this will be described when we talk about integrator rate laws. And so once again, we're working with a general equation such that coefficient A or coefficient alpha, I'm sorry, such that alpha is going to represent the coefficient for reactant A. And once again, this reactant A is going to undergo some type of decay to produce products. Now, when we're writing the general rate law for second order kinetics, the rate of the chemical reaction is equal to the rate constant K times this by the concentration of reactant A. And once again, reactant A is going to represent any type of reactant. And since this is second order kinetics, that tells us that the order of reaction is 2. And so, very similar to what we addressed in a couple previous slide, what does it mean for a reactant or a reaction to follow second order kinetics? And so once again, we can go ahead and illustrate the effect of second order kinetics, or what it means to be second order kinetics, if we plug in the concentration, if we plug in different changes in concentration of reactant A into this general rate law that is written. And so we're going to assume that this specific reactant is going to represent reactant A. And so if the concentration of reactant A is equal to 1.0 molar, the rate of the chemical reaction is equal to the rate constant K times this by the concentration of 1.0 raised to the second power. And since we're talking about relative rates, we can go ahead and exclude the rate constant K. And so this is just giving us an idea of how the rate of reaction is changing based on differing concentrations of the reactant. And so if I were to take 1 squared, that's going to give me 1.0 molar per second. So that's going to give me a baseline. Now, if I were to double the concentration of reactant A, how will the rate of reaction change? So therefore, the rate of reaction is equal to the rate constant K times this by 2.0 raised to the second power. And once again, we're going to go ahead and exclude the rate constant K since it's a constant. And by doing so, we're able to understand that if you double the concentration of the reaction, you quadruple the rate of the reaction. So notice how there's a change between the concentration of the reactant to the rate of reaction. If you double the concentration, you quadruple the rate of reaction. Now in first order kinetics, if you double the concentration, you double the rate of reaction. So notice that there's already a change. There's already a difference between first order and second order kinetics. And so here, if we were to plug in 3.0 molar into, where A is found in this general rate law, and if we exclude K, then the rate of reaction is going to be 9.0 molarity per second. And if we apply that same logic to a concentration of 4.0, this is going to be 16.0 molarity per second. And so what is this trend telling us? This is telling us that we have this exponential increase of the rate of reaction if we change the concentration of the reactant. So for example, if we double the concentration of the reactant, we quadruple the rate of the reaction. If we triple the concentration of the reactant, the rate of reaction increases by 9-fold. And if we quadruple the concentration, then the rate of reaction increases by a factor of 16. And so this trend that's observed is very unique to second order kinetics that's not observed in first order or zero order kinetics. All right, and so basically what I typed over here is what I just said verbally a few moments ago. Now, what we're going to look at is how the kinetic data looks like for second order reactions. And once again, we are going to look at it, the kinetic data in terms of concentration versus time. And so it turns out that if you plot a concentration versus time graph for second order reactions, you still get this exponential decrease very similar to first order. However, it is much steeper than first order graphs where concentration is plotted against time. And so I'm just going to go ahead and kind of zoom in here. And so you guys might not be able to see it, but let me see if I can zoom out. So go ahead and take a mental shot of how this this graph kind of curves. And I'm going to quickly zoom or quickly move over to first order graphs. So notice how it's still an exponential decay, but the steepness of the curve for first order is not as it's not as steep as second order kinetics. All right. And so once again, if we were just to take a look at the concentration of reactant A and plot it against time, we get a steeper exponential decay. And so we can get a deeper understanding of second order kinetics if we shift our focus, if we shift our perspectives and look at how the half-lives changes. And so remember that the half-life describes the amount of time it takes, for the concentration to reach half of its original value. And so if we are taking a look at the original value, which in this case is going to be 0.20, so you can associate this as 100% reactant. Half of 0.20 is 0.10, so this is 50%. Okay. And so I want to know how long it'll take for the concentration of reactant A to go from 0.20 all the way to 0.10. And I can figure that out by extrapolating a line until it hits the actual green curve. Then I'm going to go ahead and trace this back down. All right. Let me see here. Let me see if I can do it more accurately. How come it's not doing it for me? All right. Well, whatever. And so I'll just go ahead and put it somewhere right here. Okay. And so let's just say that this line, it's kind of skewed to the left, and so it's a little bit off. Somehow I can't get my my pen to draw it exactly half, but let's just say that it's 50. Okay. So it turns out that it takes 50 seconds for the original concentration to reach half of its value, to go from 0.20 to 0.10. Okay, so I'm going to go ahead and say that from 0 to 50 is going to be the first half-life. And it took about 50 seconds, which is great. Now, the only type of, how do I say this? So the relevance of looking at it in terms of half-life is if we look at the consecutive half-lives for second order. And so if the original concentration, if the new original concentration is now 0.10 instead of 0.20, we want to figure out the amount of time it'll take to reach its second half-life. What would be the time interval? And so this half of 0.10 is 0.05. And so if I take my line, my black line, and kind of extrapolate it until it hits the green graph, the green line. And if I were to trace it down so that it hits the x-axis, which represents time, notice that it now hits 150 seconds. And so if you guys are looking at the time interval between first half-life and second half-life, the time interval is going to be 100 seconds. And so if we do that for the third half-life, so half of 0.05 is 0.025, so let's just say it's somewhere over here. Let's see if my pen kind of hits it. It kind of doesn't, but that's okay. Now, if you guys are looking at the interval of the third half-life, already you can see that it's much greater than the previous two half-lives. So this is the second half-life, and this is going to be the third half-life. Okay, so it looks like for second order, as you go from one half-life to the next, and the next, and the next, the amount of time it takes for the concentration to reach half of its value, half of its original value, takes longer and longer and longer. And that is characteristic of second order. All right, and so long story short, the time interval for each consecutive half-life for second order is longer than the previous. And what we want to understand is why. Why does it take much longer to reach the next half-life, whereas in first order, the consecutive half-lives are the same? Well, that can be explained by looking at the equation for second order half-life. So notice that the half-life T1 half is equal to 1 over the rate constant K times this by the concentration of reactant A. Now, I do want to say that this 0 will represent initial concentration. And so if it's 0, then this is talking about the first half-life. Now, if you guys are talking about consecutive half-lives, then it'll be T1 half is equal to 1 over K. And then I'm just going to go ahead and leave it as, I'm not going to put this 0 here, right? So I'm not going to put that there. So this is just referring to the concentration at any given time value. And so I guess I'll just go ahead and represent this as, no, it's right, at any time value. Okay. So in other words, if you don't have this not, the 0, you're just communicating to the reader that it's not representing the first half-life, or it could represent the first half-life. Anyways, let's go ahead and go back to the main point. So the reason why the consecutive half-life for second order is much longer than the previous is because the concentration of reactant is present in the equation for half-life. Okay. And so basically, since the reactant, the concentration of the reactant is present in the half-life equation, that's telling us that the half-life, the time it takes for the concentration to reach half of its initial original value, is concentration dependent. And so because it's concentration dependent, this is telling us that all consecutive half-lives will not be the same compared to the first half-life. And this is already observed. We can already see it by looking at this graph. And so what this is telling us is that for second order reactions, if we have a high concentration of reactant, all of them are going to collide and undergo the chemical reaction very quickly. But as you deplete the concentration, then it takes a longer period of time for the reactants to be converted to products to reach until it reaches half of its initial concentration. All right, so there's some other things that we can infer just by looking at the relationship between T1 half or the half-life and the concentration of the reactant. Notice that on this equation, they are inversely proportional to each other. And so therefore, if the concentration of A is large, in other words, you have an abundance of reactant particles, then the half-life is going to be quick and short. Once again, they're inversely proportional to each other. So if the concentration of A is large, then the half-life is short, is small. Conversely, if the concentration of reactant A is small, meaning there's few reactant particles that's present, then the half-life is going to be much longer. Okay? And so that's a trend that can be observed simply by looking at the relationship of the concentration of the reactant and that of the half-life. They're inversely proportional to each other. And so when we're talking about the units for the rate constant K, which also helps us determine whether or not it's first order, second order, or zero order, we're going to go ahead and take the equation T1 half is equal to 1 over the rate constant K times this by the concentration of A. And if I wanted to look at this equation based simply on units, this equation then translates to time or seconds, right? So the T1 half is going to be replaced by time, which is seconds, equals to 1 over K times this by molarity. And so notice that the unit that this reactant represents is molarity. Okay? So I'm just replacing these terms with their units. And so if I wanted to solve for K, I'm basically going to multiply K to the other side and then divide seconds. So I'm basically switching their positions. And so the unit for rate constant K is going to equal to 1 over molarity times second. And so this is going to be the unit for the rate constant K if it's following second order kinetics, right? And so if you guys compare that to first order, it's just 1 per second. That would be the unit for K. Okay. All right, and so you guys have a lot of characteristics that can help you determine if the reaction is following second order. You guys can look at how the concentration changes. So basically, if the concentration doubles, then you quadruple the rate of reactant, or the rate of reaction. You guys can look at it in terms of half-lives. So if the consecutive half-lives gets longer and longer and longer, then that's indicative of second order kinetics. You guys can also use the half-life equation to determine if it's second order or first order or zero order. So if the half-life is 1 over the rate constant K times out by the concentration of reactant A, then that's going to tell us that this reaction is going to undergo or follow second order kinetics. Last but not least, the units of K can also tell us if this reaction is going to undergo second order kinetics. All right, and so there's a lot of examples for second order reactions, and so typically the second order reactions, the rate is dependent upon two concentration terms, and so those concentration terms can either be two components reacting with each other. In other words, if you have two components, that's representing like A plus B to produce products. or one component reacting with itself. In other words, A decomposing to products. Now, the type of second order reactions that we're studying in this chapter is only one component. We're only looking at this. We are not going to consider second order reactions for two components, for two different reactants. The equation changes, and you guys will see this when we talk about integrator rate laws. And so, for example, if you have this hydroiodic acid, and if they are reacting, or hydrogen iodide, I'm thinking that this is going to be gaseous in phase, so it's going to be hydrogen iodide. So basically, this reaction is dependent on the collision of two HI molecules, not the decomposition of one HI molecule. And so overall, this would be the rate law for second order reaction. All right, so let's go ahead and talk about zero order kinetics. And once again, we're only focused on one reactant. And so we're going to take alpha to be the coefficient for reactant A, and reactant A is going to undergo some type of reaction to produce products. And so the rate law for a zero order reaction is going to be the rate of reaction is equal to the rate constant K times this by the concentration of A raised to the 0 power. And so zero order kinetics tells us that the order of reaction is 0. Now, if you are familiar with exponents and what it does to numbers, if you raise anything to the 0 power, all of this becomes 1. And so we can rewrite the rate law for zero order kinetics to be rate is equal to K, the rate constant K, times this by 1, or simply the rate is equal to the rate constant K. And so what does this mean? So what does a zero order kinetics mean? And so if you are looking at changes in concentration of reactant A against the relative rate of the reaction, we'll better understand what it means for a chemical reaction to be zero order. And so very similar to what we've done in the prior two orders of reaction, first and second, we're going to assume that this concentration, 1.0 molar, 2.0 molar, 3.0 molar, 4.0 molar, is going to represent the reactant. And so if the rate law for zero order kinetics is simply rate is equal to K, notice that there is no concentration of a term that's in this rate law. And so what that's telling us is that zero order kinetics is concentration independent. So the reactant, the concentration of the reactant, I'm sorry, the rate of the reaction is independent of the concentration of the reactant. Okay. In other words, if you were to, let's do a baseline real quick. So if I plug in 1.0 molar into this equation, since there's no A term, the rate is going to be constant, right? So remember, with relative rate, we're just going to ignore this. So therefore, the rate is going to be 1.0 molarity per second. If we double the concentration, once again, since there's no A term in my rate law is going to be the same. It's going to be 1.0 molarity per second. If you triple the concentration, the relative rate is still going to be 1.0 molarity per second. If you quadruple the concentration, the rate is going to be 1.0 molarity per second. And so this is telling us overall that because the exponent for zero order is 0, doubling, tripling, quadrupling, etc., the concentration of reactant will not affect or change the rate of reaction at all. So the rate of reaction remains constant regardless of how you change the concentration of the reactant. And so that is characteristic of zero order kinetics. Now, if we're taking a look at the kinetic data in terms of a concentration versus time graph, since zero order kinetics is independent of the concentration of reactant, what we get is not an exponential decay, rather just a negative slope. And so this is basically what your concentration against time graph looks like for zero order kinetics. And so you guys can do compare and contrasts between first, zero, and second order with respect to the concentration versus time graph. Now, if you guys are looking at half-lives, if we go from 0.20, which is 100% in this scenario, to 50%, which is 0.10, notice that the half-life, the first half-life, if I were to trace this down, is somewhere, let me see here, somewhere in the middle of 30 and 35. So let's just say 32.5 seconds. So this is going to represent the first half-life. Okay. Now, if you guys look at the second half-life, we're going from 32.5 to 50 seconds. And so notice that the time interval gets shorter and shorter. And if we look at the third half-life, okay, notice that it's about, it's somewhere in between 55 and 60. So, or maybe leaning closer towards 60, who knows. So let's just say that it's 57.5. And so here, if you look at the third half-life, it takes about 7.5 seconds. And so when you look at the second half-life, okay, let's see here, it's going to take about 17.5 seconds. Okay. And so the first half-life takes about 32.5 seconds. Okay. All right, so I want you guys to notice that the consecutive half-lives for zero order decreases, whereas in second order it increases. For first order, it remains constant. Okay, so that's a specific characteristic for zero order kinetics if you guys are looking at it under the perspective of half-lives. And so each consecutive half-life is shorter than the previous half-life, and what we want to ask is why. And so to answer that question, we're going to go ahead and take a look at the equation for zero order half-life. And so the half-life under zero order is going to be the concentration of the reactant A divided by 2 times the rate constant K. And so I want you guys to notice that the half-life is on the same, they're both in numerators. So for example, if I have T1 half over 1 is equal to concentration of A over 2K, So I want you guys to notice that the half-life is in the numerator and the concentration of A is in the numerator. So therefore, the half-life is proportional to the concentration. And so for a zero-order half-life, the concentration, the half-life is dependent on concentration, very similar to second order, right? However, the rate law is independent of the concentration of the reactant. So the half-life for zero order is still dependent on the concentration of reactant A. Okay. And so anyways, since the relationship between half-life and concentration of A is proportional, that means that if the concentration of the reactant decreases, the half-life also decreases, which is what was observed here. So notice how as the concentration decreases, the half-life, the amount of time it takes for the concentration to reach half of its original value, is also decreasing. Okay. And so let's go ahead and take a look at the units for the rate constant K for zero order. So we're going to go ahead and take this equation. So T1 half is equal to the concentration of A raised to, divided by 2 times the rate constant K. And so what I'm going to do is I'm going to replace all of these terms to the unit that they represent. And so half-life is time. And so for now, I'm going to associate time as seconds. And I know that this bracket is going to represent molarity. Now 2 is a constant, so that's 1 essentially, right? I'm just going to basically take this out, times this by K. And so if I solve for K, that means I'm just going to switch places. I'm going to multiply K to the opposite side, and then I'm going to divide S to the opposite side. So they're swapping places. The units for the rate constant K for zero order is simply going to be molarity per second. Okay. So this is different than second order. Remember, second order is 1 per molarity times second. And this is also different than first order, which is 1 per second. So overall, zero order processes, the rate is fixed. And the rate of the reaction is independent of the concentration that is present. However, the half-life for zero order kinetics is still dependent on the concentration. And so as the concentration decreases, the half-life also decreases. And that's one of the main points you guys should take away. And so what's an example of a zero order reaction? One example of zero order reactions takes place biologically. And so you guys have this macromolecule that's composed of proteins, and it's known as an enzyme. An enzyme catalyzes a reaction. So you have these little pink circles, they're known as substrates. And for the substrate or the reactant to be converted into their product, the enzyme has to be the one that catalyzes that reaction. And so basically, if you have 5 enzymes, it doesn't matter how many reactant particles or substrate particles you have. If it's saturated, much like in this scenario over here, if you have a high abundance of your substrate, if you only have 5 enzymes, then the rate of the chemical reaction is going to be dictated by the number of enzymes that's present in the solution or in your body. Okay, so the turnover rate is dictated specifically by the enzyme. All right, and so let's go ahead and understand the relationship between half-lives and concentration. Okay, and so notice that once again, if you have a high concentration, and as you decrease that concentration by 50%, and if you compare that first half-life with the second half-life, ooh, what's happening? So if we're starting at a lower concentration and we're going to an even lower concentration, the amount of time it takes is going to be much shorter than the first. So you guys can imagine this. You guys can imagine this scenario by looking at this diagram. And so if you guys have a high concentration of substrate, the amount of time it takes for those enzymes to decrease the concentration of the substrates by 50% will take a longer period of time compared to if you have a lower amount of substrate or a lower amount of reactant. So for example, if you only have 2 substrates, the amount of time it takes to reach half of the initial concentration will be much, much faster than a situation in which the enzymes has a lot of substrates to work with. Okay. All right, so hopefully that makes sense. All right, so what we're going to do is we're going to go ahead and, so I'm going to go ahead and go back a few slides here. So now that we have covered some basic characteristics of what it means to be first order, second order, and zero order kinetics, we're going to go ahead and revisit this idea of rate law. And we're going to now take a look at what would happen if we integrated the rate laws. And so once again, the rate law provides information about how the rate of the reaction changes based on the concentration of changes in concentration of the reactant. However, the rate law does not tell us, how much reactant remains after a period of time has passed. And so sometimes, we would like to answer that type of question. So what is the concentration of this reactant at some period in time? Or maybe perhaps we want to figure out what % of the reactant has been consumed after a period of time, or how much time has elapsed before the reaction is 50% complete, which implies half-lives. Anyways, all of these questions kind of probe the relationship between concentration and time. And so the rate law itself does not have units of time. And so for us to understand the relationship between concentration and time, we will have to perform some calculus. Basically, we are going to integrate this rate law. And so I wouldn't worry too much about the math behind the integration. That's really not the main point of this chapter. And so if you guys are, have done calculus, you guys know what it means to integrate a mathematical equation. And so I'm just going to go ahead and kind of jump the gun here. So this is an overall quote-unquote cheat sheet, if you will, that summarizes the half-lives for first order, second order, and zero order. And so this is something that we've already seen in prior slides. And so what I want to go over is the integrator rate laws. And so basically the first order integrated rate law looks something like this. The second order integrated rate law looks something like this. And the zero order integrated rate law looks something like this. And so I want you guys to notice that in the integrator rate laws, when the rate law is integrated, notice that there is now a connection between the concentration and time. Concentration and time. Concentration and time. Okay. And so before we go through the details of this, let's go ahead and take a look at some of these variables and let's figure out what it means. So this T it's notice how the half is not present. So this t is not representing half-life. This is just representing any period of time. And k is going to represent the rate constant. Okay, and so go ahead and scribble this out, so don't worry about this. And so this rate constant is the same as this rate constant. So the rate constant k allows us to connect this idea of half-life to integrated rate laws. Now, we know that this bracket represents concentration, so this is concentration of reactant A. Now, if you have this 0 or this naught, that's representing initial concentration. And if you have this T, that's representing the concentration at any time. So concentration at any time. Okay. So if we look at the second order rate law, all of the pieces, are the same. So this T is any time, K is the rate constant K, which is the same as this rate constant K for second order half-life. So this B is representing, so instead of B, you guys can just say A, right? So instead of B, you can say A for consistency. Okay. And so this is basically telling us that this is the initial concentration versus concentration of the reactant at some period of time. Same thing here, initial concentration, concentration of that reactant at any given period of time. So for zero order, the integrator rate law looks something like this, where you have initial concentration, you have time, you have rate constant K, and then you have the concentration of that reactant at any given period of time, where the where the rate constant K is the same as this rate constant K. And this A naught, I'm just going to X this out, is just going to represent, any concentration, regardless if it's initial concentration or concentration at any given moment in time. Okay, so same here. Okay. All right. So overall, these are your integrated rate laws, and you don't really need to worry about how to integrate the rate law to produce these equations. So you guys can go ahead and just copy them down, put it on your cheat sheet, if you will, put it in your notes, make sure you guys have them. So the one thing about these integrated rate laws is that first order equations is very specific. So if you were to, on the exam, misassociate first order as this, then you are going to be wrong in your answer. So you just want to make sure that you are familiar with which equation represents first order, which equation represents second order, which equation represents zero order. So remember that when we were discussing first order, second order, and zero order kinetics, I was constantly referring that the general reaction is only one reactant. And so this is basically summarizing what the differential equation looks like for zero, first, and second order. And so this is the differential equation. And when we integrate the differential equation, we get the equations that I've shown you here. Okay. And so this is their corresponding half-life. And so the main reason why we're only looking at one reactant to produce some product is because if we, for instance, have two reactants, so in other words, if we have A plus B to produce products, so I'll just put in, alpha A to produce products. Okay, so this is the overall chemical equation we're describing. Look at the integrated rate equation. It becomes much, much more complex. And if you look at the half-life, it also becomes much, much more complex. If we're talking about third order reactions, whether the equation is just going to be A, decomposing, or, A plus B. Okay, so I want you guys to look at the integrated rate law equation. And I want you guys to look at the half-lives that's associated to these integrated rate law equations. They become much, much more complex, which is out of the scope for this course. And so it's important for us to understand that we're working in this semester with only very simple chemical equations, typically just one reactant. And if it becomes much more complex, then we get much more complex equations. All right. And so I'm going to keep on scrolling here. Where is it? Oh, okay. All right. So let's go ahead and continue with our discussion of integrated rate laws. So I want you guys to recall that the rate law for first order is going to be rate of reaction is equal to some rate constant K times this by the concentration of A raised to the first power. Now if we integrate this rate law, so this is the symbol of integration, this expanded S, what we're going to eventually get, and I'm not going to show you guys the proof. If you guys want to see the proof, feel free to Google it. This is not a calculus-based course. So if I integrate the rate law, I get the natural log of the concentration of A at any time period over the initial concentration. Okay, so this is representing initial concentration. And that's going to equal to negative KT. Okay. So this is one form of the integrated rate law that you guys can use. And so it turns out that the integrated rate law can actually help us determine whether or not a chemical reaction is undergoing first order, second order, or zero order kinetics. And so this can be done by rearranging the integrated rate law to create a straight line equation. And by plotting this straight line, what we get is a straight line plot. And depending on the result of the straight line plot, it's going to confirm whether or not the chemical reaction is undergoing first order, second order, or zero order kinetics. Okay? And so this is going to be another way for you to characterize whether or not the reaction is first order, second order, or zero order. Okay? So what I'm going to do is I'm going to take this equation. So let me see if I can just duplicate it. Okay. And I'm going to expand this. And so when I expand this, basically I'm distributing that natural log. And so if you follow the properties, if you are familiar with the properties of natural log, if you're dividing two items, you can subtract them through expansion. And so the natural log of A sub t at any given time period minus the natural log of the initial concentration is equal to negative K times T. And so what I'm going to do is I'm going to take this term and I'm going to move it over to the other side so that I get the natural log of the concentration of A at any given time period is equal to negative K times T plus the natural log of the initial concentration. And so if you were to expand your first order kinetics integrated rate law equation, what you get is this straight line plot, or what you guys get is this equation. And so the reason why I keep on referring to this equation as a straight line is because if you overlap the equation of a line, y equals to m times x plus b, this is telling us that if the y-axis represents the natural log of the concentration, and if you plot that against t or time, what you're going to get is a straight line such that the slope m equals to the rate constant k, and the y-intercept is going to equal to the natural log of the initial concentration. And so if I were to plot this, equation, I get a straight line that looks like this. So I get a straight line that's going down, so this is a negative slope. Now, what you want to pay attention to is the units for the axis. So this is, all of these numbers are representing the natural log of the concentration of A. So if you plot the natural log of concentration of A against time, and if you guys get a straight line going down such that the slope is negative, then this is a confirmation that the reaction is undergoing first order kinetics. Okay. Now, let's go ahead and talk about second order kinetics. And so recall that the rate law for second order is rate is equal to k times this by the concentration of A raised to the second power. And so if you were to integrate this rate law, you would get a result of 1 over concentration of A at some time period minus the minus 1 over the concentration of A at the initial time period. So basically this is representing initial concentration. And A sub t is representing concentration at any given period of time. And so all of this is going to equal to kT, positive kT, positive rate constant K, times that by t or time. And so you guys can go ahead and use this form for working through word problems, etc. Now, if you wanted to confirm whether or not the chemical reaction is undergoing second order kinetics, we need to go ahead and move some terms around such that 1 over A sub t, let's see here, I'll just go ahead and just rewrite this. Okay, so basically what I'm going to do is I'm going to take this term and I'm going to move it to the other side such that I get 1 over A sub t equals to kT plus 1 over initial concentration. And so if I were to overlap this resulting equation with the equation of a line, which is y equals mx plus b, notice that I get the y-axis to be 1 over the concentration of the reactant A. So in other words, the reciprocal of the concentration. My slope is going to be a positive value because this K is now positive instead of a negative. And my x-axis is going to be time. And my y-intercept is going to be the reciprocal of the initial concentration. And so if I were to plot this on a graph, I will get a trend that looks like this. And so if you take the reciprocal of the concentration, so basically all of these numbers were the result of the reciprocal of the concentration. And if you plot that against time, and if you guys get a positive slope, a positive straight line, then this is a confirmation that your chemical reaction is undergoing second order kinetics. Okay? So you have all of these different characteristics that will inform the reader or the scientist whether or not the order of reaction is first, zero, or second order. Okay. So let's go ahead and finish up this lecture by looking at zero order kinetics. So once again, for zero order kinetics, we have a rate law such that the rate of the reaction is equal to the rate constant K times this by the concentration of A raised to the 0 power. And so if we were to integrate this rate law equation, so we're performing calculus on this rate law equation, which you guys don't need to know. The integrated rate law is going to be the concentration of A at any given time period minus the concentration of A at the initial time period. So once again, this is representing initial concentration, and A sub t is representing the concentration at any given time period. That's going to equal to negative K times T. And so if I were to, I'm going to duplicate this so I don't have to rewrite this again. All right, so very quickly, you guys can go ahead and use this integrated rate law to determine the remaining amount of time, or I'm sorry, the remaining amount of concentration of the reactant after a certain time has passed or something like that. And we'll go ahead and take a look at these equations in greater detail when we apply them to word problems. So if I wanted to test whether or not my chemical reaction is undergoing zero order, I'm going to go ahead and quickly move this to the other side. So I'm adding, so I have the concentration of A sub t is equal to negative K times T plus the concentration of the, plus the initial concentration of the reactant. That's what A sub 0 represents. And so if I were to overlap this by the equation of the line y equals mx plus b, I can see that if I plot concentration against t or time, which is my x-axis, my slope is going to be negative, whereas my y-intercept is going to be the initial concentration of A. And so what I get is a graph that looks like this. And so if you guys are trying to determine if a chemical reaction is first order, second order, or zero order, if you plot the concentration against time, and if you get a straight line going down such that the rate constant K is equal to the negative slope, then this is going to be a confirmation that the chemical reaction is undergoing zero order kinetics. Okay. All right, so that's pretty much it for this lecture video. The next 2 or 3 lecture videos, we're going to go through applications of integrated rate laws. So everything that you guys learned here is just the background information, just the theory of what it means to be first, zero, and second order. And so what we're going to do now is we're going to take all of this information and apply it in terms of a word problem setting, which is going to be relevant on your guys' exam. All right, so the next few videos are optional. This lecture will be posted on Canvas, so you guys can just look through my work. But if you guys want the commentaries, if you guys want me to work it out, feel free to watch those next few videos. All right, catch you guys later. Bye.